Okay, so in this video, we're going to talk a little bit more about energy and chemical reactions, and we're also going to start to talk a little bit about enzymes. So to start with, here's a reaction shown on this slide, and we're looking at the breakdown of glucose into carbon dioxide and water. All right, so looking at this chemical reaction, there's a question on here: which side of the reaction is more stable, the glucose and the oxygen or the CO2 and the H2O? To answer that question, you're going to look at the molecules and try and decide which is bigger and more complicated and has more bonds and is more complex. That one's going to have more energy in it and therefore be less stable. And the side of the reaction that has smaller, less complicated, less complex, less organized molecules is going to be less energy, but therefore more stable. And if we look at this overall, glucose is a pretty big molecule here. It's got lots of bonds, whereas over here we have CO2 and H2O, very small, simple molecules. So in this equation, on this reaction, this is more stable and has less energy. All right. Okay, so this is a reaction going from high energy to low energy. So really this would be considered exergonic. Energy is going to come out. And based on what we've already talked about, this would be a reaction that is following the second law of thermodynamics, which says that the universe wants things to go to be more stable. All right, so that's all good. But the next question is, does this reaction occur spontaneously, or does this just happen? So if you had a bunch of sugar, a bunch of glucose in your hand, would it just automatically turn into carbon dioxide and water? I mean, you can think about your pantry in your house. You have sugar, you don't have glucose, but you have sucrose, kind of related. Does the sugar in your pantry just poof turn into CO2 and H2O over time? No, it doesn't, thankfully. It stays in your pantry. Once you bought it, it stays there till you use it, right? So this reaction, the breakdown of sugar into CO2 and H2O, doesn't just happen, even though if I was going to draw a reaction diagram, an energy diagram for this reaction, it would be like this, right? The reactants are up here. This is the glucose, so it has high energy, and this is be the CO2 and the H2O. They have low energy. So it looks like this is a downhill reaction. It should just go, but it doesn't just spontaneously occur. Something is stopping the glucose from just rolling down the hill and turning into CO2 and H2O energetically. All right, so let's look at what's going on here. So the reason why this reaction doesn't happen spontaneously is that in the glucose molecule, all those atoms, all those C's and O's and H atoms are engaging in covalent bonds, and they're sharing electron pairs so that all their outer shells are filled and they're stable, and they are, I mean, for want of a better term, happy. They're not happy, they don't have feelings, but we like to say, in this molecule, all the atoms have full outer shells because they're sharing electrons to get to that point. All the carbons are making 4 bonds, all the oxygens are making 2 bonds, all the hydrogens are making 1 bond, etc., etc. So to be able to have this glucose molecule rearrange itself into carbon dioxide and water molecules, we have to disrupt those covalent bonds. We have to convince those atoms to separate from each other and lose their shared electron pairs. Or not lose the electrons, but break that sharing. And so to do that, you have to put energy in to break the bonds apart to start with. We have to destabilize this structure of glucose and these oxygen molecules as well. And the energy that you put in to get that destabilization is called the energy of activation. And we write E with a little a down here. The A stands for activation. So energy of activation is the energy you have to put into a chemical reaction to get it to start. Even if overall the reaction is going to give off energy or release energy like an exergonic reaction will, overall it gives off energy, there still has to be some energy input at the beginning. And that energy input is termed the energy of activation. And I have a slide that kind of demonstrates that a little bit here. So on this slide, I've not got glucose. Instead, over here we have the reactants. Here we have ethanol. So this is the alcohol, that same stuff that's like in hand sanitizer and stuff. So ethanol molecules. This could just as easily be the glucose that we saw on the previous slide. So we could have glucose here too. But you can see the atoms. There's a carbon atom there. It's bonded to some hydrogens and another carbon. And then there's a bunch of chemical bonds happening to hold this ethanol molecule together. And here is the oxygen that we're going to need as well for this reaction. And so overall, if we added up all the energy that are in these bonds and these bonds, it would sort of be this much energy. All right, so the energy of reactants on my energy diagram is coming in at here. Is this much energy, right? And then the overall, to get this reaction to go, we're going to have to put some energy in. And that's why this curve is going up, right? We're putting energy in. The energy is going up. And as we go up here, what's happening is all these atoms are being broken apart, bonds are being broken. So now all the carbons are separated, and all the hydrogens are separated. I don't know how many there are. I'm probably not drawing enough. We need to draw some blue oxygens. That's not a very good blue, but so what we're doing here is you put energy in to the reaction to break apart all these bonds. And here we are at the top of the curve. Up here, things are very, very, very unstable. None of these atoms have full outer shells. They're like, oh my gosh, I used to be bonded in this beautiful molecule and all my valent shells were filled and everything was stable and I was pretty happy. But then energy got put into me, everything broke apart, and this is not a good situation to be in. I don't like it up here. I'm teetering on the top of this hill and I could fall in either direction, roll off the hill. Now, these atoms can then reassemble themselves as CO2 and H2O molecules. So, or they could reassemble themselves. So they could fall down the hill this way and reassemble themselves as CO2 and H2O, or they could fall down the hill this way and reassemble themselves as ethanol and oxygen. Theoretically, they could go both directions because both of those structures work, but the second law of thermodynamics tells us that the universe wants to be stable. It's always trying to get to the more stable situation. So these atoms at the top here are always going to fall in this direction to the lower point, which is the CO2 and the H2O. So they'll rearrange themselves as a bunch of CO2 molecules and a bunch of H2O molecules. And these are the products of the reaction. So you can see overall, the reactants are up here and the energy and the products are down here. So overall, energy came out. So we can say here, energy is released. So this makes this an exergonic reaction. But for that energy to be completely come out, we had to put a little bit of energy in at the beginning, all right, to get up to this point. So this amount of energy that we put in from here to here, we had to put in this much energy. This much energy is called the energy of activation. All right. So here's a nicer diagram of what we've just been talking about. So you can see kind of drawn in properly. The ethanol starts over here. These are the reactants. I put in the energy of activation to get to the destabilized situation at the top of the hill. And then these atoms can rearrange themselves all the way down here as water and carbon dioxide, and these molecules have less energy stored in them overall. The E chemical here on this right side is lower than the E chemical here. So overall, we can still say this is exergonic because we're going down a hill, even though we had to go up a little hill to get everything started. And in this diagram, the energy of activation is this here. Okay, so it's interesting. Some chemical reactions go very, very easily. So things, burning stuff like burning paper, burning alcohol. Alcohol sets on fire very, very easily. So like the energy of activation, you don't have to put much energy in for it to go. So the hump here isn't very high, right? This is a low, this is a reaction that doesn't need much activation energy to get going. But something that's very hard to make the chemical reaction go, like something that's doesn't burn well, something that's like fire retardant or whatever, it would look like this. Here's the reactants. You've got to put so much energy to get it going that it's really, you've got to put a lot of energy of activation in to get this reaction going. So it's not going to go very easily. This would be a chemical reaction that's very resistant to going, or something that doesn't burst into flames very easily, right? So different reactions have different levels of activation energy.